All right. Well, just like we can form factor groups or quotient groups, we can do quotient rings when you have an ideal. So normal subgroups are like ideals. So if you have an ideal, you can define to be the set of right cosets. It's called a factor or quotient ring. It might be a quotient ring. And the addition is exactly like what you'd expect, and the multiplication is exactly what you'd expect. It pretty clearly defines an abelian group. Why is that? Because R is an abelian group. Ideals are normal subgroups because they're sub-rings, or they're sub-rungs, but that forms a subgroup under addition, and since the addition is commutative, so this is an abelian group, and so you have normal subgroups. So we definitely have, this works out just fine from what we know about groups. That's just groups. So the main thing is to talk about what's going on here. Identity is I, you have inverse. Yep, and this holds, or otherwise you can just think of it as we're just working with groups. We're ignoring the ring structure, we're just looking at the abelian group structure. So we need to show that the multiplication is associative and closed, and that you have the two distributive laws. So, three things in there. Let's see if we have associativity. That's equal to that by definition. Oh, we get that. Oh, but remember, we're in a ring, and these are ring elements. So we have associativity for the ring. Like that, and then we just unravel it. Like that, like that. And now we can show that's closed, and then it's definitely closed, because when I multiply them together, I get this, and that's defined to be in here, because this is a right ideal. It's a right coset. And then distributive law, yeah, we can do it. Watch this. We'll just go through it. Add these two first. Now multiply those two. That. Now this is in the ring, so I can use the distributive law on this ring element. And I just unwind it now. Done. Now this is very similar. We'll just zip through it. Da-da, 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 da-da. All done. There's one more thing to check, and it probably should have been checked first, but I just want to get the main idea. This is kind of a technical detail. Cosets have multiple names, so we still need to see that things are well defined. We need to make sure that the multiplication doesn't change depending upon the name of the ideal we use, or the name of the coset we use. So let's suppose we have two different names for the same coset for each of these cosets. Okay, we're going to check to see that the addition works out. It will actually, because this is just this is a group quotient, but we'll recheck it anyway. We'll also make sure that the multiplication works out. So from what we know about cosets, right, we can rewrite these. Then when you add them together, x plus a like that, and then these just get sucked in. That's just equal to I, and that's just gets equal to I, so we get that. So addition's well defined. Let's look at multiplication. This is going to be a little bit trickier because when I multiply together these two, I'm going to get x plus a times that. So we get here. And now we're going to see why being an ideal is really useful. When I multiply this out, I get a prime b prime is equal to this mess. Oh, luckily I have the absorption property though, because x and y are in the ideal, so that's in the ideal by the absorption property. That's in the ideal by the absorption property, and that's in the ideal by the absorption property, so this is all just equal to I. Absorption property is what we're saying there. We're done. So all this gets sucked into the I, and we're just left with AB. Or a better way of saying that is I, right? We're just thinking about cosets. If you understand cosets for groups, this is just an element of I. So which coset is this? It's going to be the same as I because I is closed. Whenever I add any element of I with this thing, I just get another element of I. So I'm going to stay in I. So here's some examples. So it's a sub-rung if you don't include your unity as a ring axiom. So this is going to be an example. 2z is definitely an ideal. Why is that? Because if I take 2n times any integer, I'm going to get 2 times 2n, 2z, and that's definitely in 2z. And you can do the other side too. If z's on the other side, you're still going to get this because of multiplication's abelian. Multiplication's abelian in the integers. It might not be in other rings. Then if you quotient out, you get 2z plus 1, 2z plus 0. Those are your two elements. So you have a ring with just two elements. That's isomorphic to z2. In fact, many people define z2 to be like this. Here are the polynomials with integer coefficients. Let the ideal be that this is even, that the constant term is even, right? F of 0 means a constant term. So you should verify that this is an ideal, and maybe I'll just do that for you. Right, if you have an x to the n plus da 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 plus a1 x plus 2n, this will be the constant term. You need f of 0 is even. Here's f of 0. I didn't mean to cross it out. If I multiply this by any other polynomial, what's going to happen when I multiply it out? Well, I'm going to get a whole bunch of stuff that has an x in it, and I'm going to get the constant term, which is going to be 2n times bn, b naught. But notice that this thing's going to be even. So we have the absorption property. If I take anything in the ideal, multiply it by any other polynomial, whether it's in the ideal or not, the result is going to have an even constant term. So that means that we're back in the ideal. So we have the absorption property. This is an ideal. What happens when we quotient? So it's, again, just two elements. What happens? Either you are in the ideal, in which case it's something like x squared plus 6, or if you're not in the ideal, if you're like x squared plus 5, you're almost in the ideal. You're just one off from being in the ideal. Because look, x squared plus 4 is in the ideal. Then if you just add 1, you do that. So this is x squared plus 6 is in the ideal, and you could either add 0 to it, and that's, if you're in the ideal, you're that. If you're not in the ideal, like x squared plus 5, you take something that's in the ideal, in the I, and then you just add 1 to it. And every polynomial can be written like that. Every polynomial can be written as something in the ideal plus either 1 or 0. That's isomorphic to Z2. That's all for factorings. Thanks.